This is basically, if you like, a quick introduction to dynamics. It doesn't cover everything that is encompassed by dynamics. So it's normally a 2-day course for transient dynamics and also the other parts of dynamic solving. But here I'll sort of try to, I guess, summarise on the main points. Okay, so I'll talk about the different dynamic analysis types, time step considerations, and also how modal analysis fits into the whole picture. So I'll show you a transient simulation setup, or at least a model that's being solved, and also talk about damping, and also show you damping in a model and how it affects your results. Okay, so with a full transient or a dynamic analysis, we basically solve the full equation of motion. So it means we include any time-dependent effects of any applied forces. So our stiffness can change, it can be non-linear, and then we also include damping effects and also our inertia effects. So you can calculate the motions of bodies by using a full transient simulation. Okay, so there's different dynamic analysis types. So depending on the outputs you want, you choose any one of these. So a modal analysis you nearly always need to do whenever you do any sort of dynamic analysis. It tells you your natural frequencies. It will tell you what your dominant frequencies are, and also if you've got a particular excitation direction, what sort of frequency content will excite that particular direction. Or it might just be that you've got a machine that runs over a certain frequency range, and you want to make sure you don't have any resonances in your structure. Okay, so a harmonic analysis we use if you've got a sinusoidally varying load and you know what frequency range it sweeps over. So you can have more than one load applied at the same time, but they all operate at the same frequency. So if you had two unbalanced wheels rotating on the machine, they might be out of phase. So you apply both of those loads and you sweep through a frequency, and then you can find what your actual responses are over those frequency ranges. So a spectrum analysis and a random vibration analysis, these are both frequency domain simulations. So you take a time domain signal and you basically break it down into a frequency domain signal. So for some cases you can do that. So it's a much quicker solution. So an earthquake or driving over a rough road, you can characterise that as either a spectrum where you have a force or an acceleration versus frequency curve, or you can have a random vibration. So random vibration basically outputs the probability that your stress will exceed a certain value. So this is done as basically as a power spectral density. So things like space shuttles, it's used a lot to sort of simulate very short duration events. So you just do it as a frequency spectrum. So all of these are linear. So up to this point, everything is linear. So spectrum, random and harmonic can all be done using what's called a mode superposition method, where you reuse the modal analysis results. So any one of these signals, if you like, can be built up as a sum of your modal analysis results. So you can do that with transient as well, but in general, for transient events, you normally want to account for non-linearities in your model. So you nearly always do that as basically as a full method. So you can include all sorts of non-linearities, your contact, material non-linearities, and geometric non-linearities, because most of the time your displacements are going to be quite large, and you're calculating displacements of bodies as they're moving. Okay, so With a full transient simulation, we have this concept of a time step, because we're calculating a solution over a time duration with small time steps. So we need to make sure those time steps are small enough to capture all of the frequency content that your structure may have. So if we take just a very simple example, so easiest way to sort of explain this is to put an equation into Excel and then vary your delta t and then see how closely your plot matches what you're putting in. So because we know what this sine wave is going to look like, so we've got a frequency of 1.59 hertz, so our fundamental period is 0.62 seconds. So each dot here is basically my time that I've got in Excel to calculate the wave. So what I need to make sure of is that I have enough sampling points within this one wave to capture the shape of the wave. So if you've got a very complicated response, it might have a lot of different frequency content in there. You need to make sure that your time step is small enough to capture the highest frequency that's in your signal. So if you have a step excitation, so it might be an impulse load onto a structure, that will excite all of the natural frequencies at the same time. So all of those frequencies will go into the response of the structure. Okay, so the aim is to get 20 points per cycle, or 20 points per dominant frequency. So a period's 0.62, so this means we need a sample rate of 0.03 seconds, or close to 32 hertz. So if we're above this sample rate, we'll capture our sine wave quite accurately. So here we've got a sampling rate of 125 hertz, so you can see that curve there resembles a sine wave. Okay, so if we lower our sample rate slightly, so it still looks like a sine wave. Okay, so if we lower our sampling frequency lower than our 20 points per cycle, so here we got just under 8 points per cycle. Does that look like a sine wave anymore? No, so that means that your response isn't going to be captured accurately anymore. Okay, so if we go lower again, so this looks nowhere near a sine wave. And if we magically happen to use a sample rate that skips over the troughs, this will look like a flat response. So this means that if your time step is too big, you totally miss some frequencies in your response. Okay, and if they're quite dominant frequencies in your analysis, that means your response that you're calculating, although the solver will give you results, they may look quite believable, but they'll be totally wrong, because you've used a time step that's excluded a particular frequency. Okay, so at low sample rates we miss out on some information, but sometimes we deliberately do this because at very, very high frequencies, those high frequencies are damped out quite quickly. So if you exclude those frequencies by using a high time step, that's not going to make any difference to your results, because those frequencies will have died out quite quickly. So for most metals, you normally have some sort of damping. So very, very high frequencies get damped out very, very quickly. So there's no point trying to capture those frequencies by using a tiny time step, because that's going to increase your solution time, and it's not going to add any extra fidelity to your results. Okay, so with an impact, so as I said before, it will excite multiple frequencies. So how many frequencies do you include? So in effect, how high do we need to go in terms of what frequency content do we capture? Okay, so if we look at what a step excitation looks like, so it's basically an infinite series where you have the odd harmonics and then with ever decreasing amplitudes. So this means that your higher frequencies contribute less. So if you exclude those higher harmonics, you're not really losing any resolution of your sort of step excitation. So this sort of base period here is basically the duration of your step, and then after that step is removed, then those that frequency content will possibly be moving about in your structure. Okay, so here if we include up to the 8th harmonic, so our frequency is 30.24, so that's 19 times our base frequency. So if we want to capture up to the 8th harmonic, we need a sample rate that's basically 400 times our base frequency. So then that way we'll capture all of that frequency content. Okay, so in this example here, this is basically a structure. It's a vibrating reed tachometer. So you place this on a vibrating structure and each one of those fingers will vibrate over a certain frequency band. So if you apply a certain excitation in a particular direction, it will excite certain frequencies. So in the sort of up and down and then left to right frequencies, they'll be quite low. So the axial modes of these fingers will be quite high. So even though a modal analysis may pick up those frequencies, they may be a lot higher than the particular frequency that you're putting in to this device. Okay, so if we look at the different modes, so I'll bring this model up shortly. So up to the 9th mode, it's basically in order of the sort of up and down response. But then because this finger is a lot shorter, you start getting the transverse frequencies, and then once you get to mode 16, then the last finger has its up and down mode. Okay, so I'll just show you this model. Okay, so this has got a whole lot of linked analyses, so don't worry too much about the complexity. Okay, so the starting point for this model is a modal analysis. Okay, so here I just have a support condition at the back, and then all I'm doing here is finding the natural frequencies. So there's no external force applied. So you know, I'm just calculating the natural frequencies. Okay, so if I animate this mode, so you can see how the finger beside it is vibrating a little bit as well. Okay, so because the modes of these are sort of spaced to have some overlap, so you can sort of get a frequency range that this thing will measure. Okay, so if I sort of just do a static animation of each one of these, so as I move to the 10th one, this will go from side to side, and then it sort of, that wave sort of goes along until it picks up the 16th mode, then the rest of these fingers sort of go. Then you get the second, if you like, the second mode shape of that particular beam. Okay, so up to this point I've captured 426 hertz. So depending on the frequency range that I want to use this device in, I don't necessarily need to go any higher with my modes. Okay, so this is just a table of those frequencies. So you normally need to look at both the value and in sometimes the way that the structure is moving, because based on the expected direction of force excitation, that might not excite certain modes. So With the transverse modes, they may never be excited if my machine isn't vibrating in that particular direction. So, but in that case, because I've got those transverse modes in between, and then there's the last finger on the end having that up and down mode, I still need to capture that intermediate frequency content. So there's no way you can sort of exclude that content that will get captured. So if there is any movement in the transverse direction, even if it's insignificant, it will still be picked up, because we've used a time step to be able to capture that. Okay, so in our solution output, there's this concept of participation factor. So if I look at my geometry, so this is the Z direction. So this is basically telling me how much of my mass is participating in that particular mode. So you can see the first mode has a ratio of 1. So this has got the highest participation factor. And then there's a column on the end here, ratio of effective mass to total mass. Just tell me how much of the total mass of the structure is moving at that particular mode. So you can see our modes 10 to 15, it's pretty much 0, because there's no movement in the up and down direction. And then mode 16 all of a sudden has quite a high participation factor. So the column, or the sort of thing we're looking for from a modal analysis, is this total, or the total effective mass in a particular direction. So normally, to say that you've accounted for all of the response, you normally need this to be somewhere between 80 and 90%. But depending on how your structure is constrained, 80 or 90% of the mass might not be able to move. So that 80 to 90% is based on the entire mass of the structure. But if 50 or 60% of my mass was clamped, then it can't move. So you'll never get that 80 or 90% of the ratio of effective mass to total mass. So you need to use some judgment to decide how high do you keep going. So what you normally look for, or the characteristic you see, is that this cumulative mass fraction. So this will always be 1, because that will be based on the mode range that you have. So when this sort of jump between two modes is pretty low, that means that with each mode you're adding, you're not adding any significant amount of mass to your overall participation. So in the axial direction, so you notice there's a ratio of 1, but the ratio of effective mass to total mass is tiny, and our total percentage is quite low. So because those axial modes are going to be significantly higher than the bending modes, you're going to have to capture quite high frequencies to pick those up. And because they're quite high, it's highly likely that they'll damp out quite quickly. So there's no point even trying to capture those particular modes, because they won't be present in your response, especially if you add damping to your solution. Okay, so on the side direction, so you can see that the ones that are quite high in the up-down are basically 0. So it's basically, you're sort of swapping over. So up to the 20th mode, so you can sort of see that with the animations, that our responses were predominantly in the X and Z directions. Okay, so if we apply the step excitation in the axial direction, you have to have quite small time steps to capture that response, even in an undamped solution. Okay, so because we're using small or tiny time steps, your solve time is going to be significant. So this is why you'd never jump straight into a transient simulation without first understanding the modal behaviour of your structure. Okay, so if we basically put an excitation on each finger. So basically I'm moving the finger down and letting go, and then it will sort of vibrate, and then depending on whether or not I've got damping, that finger will eventually come to rest. So we talked about load steps yesterday. So here we've got our basic table of our load setup. So when I'm moving the finger down, I don't need to account for time effects. So here we can turn off time integration. So basically we're switching off our mass and our damping terms, and then we switch them back on in the third and fourth time step. So this is a way of sort of mixing a quasi-static with a transient in one solution. So you can, so normally after you've switched them on, I've not seen them sort of switched off. So generally if you like it's almost like a preload step, or getting your initial conditions imposed on a transient, you can do that with time integration off. So this is a much more efficient in terms of solve time solution. So in these steps here, you still need to use the same sort of time steps to capture the dynamic response. But because we're not interested in that as we're moving the fingers down, it doesn't make any difference on whether we include those effects or not, with the added benefit of it taking a shorter time to solve those first two load steps. Okay, so here this is basically a plot of the response. So this doesn't have any damping. This is the directional deformation, so it's pushed down, it's held, and it's let go. So it will sort of keep oscillating about a mean value. Okay, so in general we'll have some sort of damping. Okay, so there's different ways of applying that damping. Okay, so you can have actual damper elements. So if I look back at my model, so on the end of each sort of finger you can put a spring element that's just got damping, and that will damp out the response. Or what we can do within the solver settings. Okay, so this one doesn't have damping. Okay, so if I look at all of my responses here, okay, so you can see that one there. So you can see that there's a little bit of sort of almost like some phasing going on. Okay, so when we include damping, okay, so you can see that the response dies off. So depending on what sort of damping I apply, so I think here I've used so I've chosen a particular frequency, and then I know the damping ratio at that frequency, and then it will calculate the damping coefficient. Okay, so here we're basically specifying it's based off a certain value, but the damping ratio will vary with frequency. You can put a constant damping ratio that is sort of constant across the whole frequency range, but in general at higher frequencies you normally have the damping ratio will be higher, because this stiffness coefficient, just off the side of the page there, so that will be, it's normally a constant value, but normally you can base it off a certain frequency, or if you want to damp out a particular frequency, you can do it the opposite way. You can say, okay, I think a frequency of 100 is the base one that I want to damp out, and then you choose your damping ratio appropriately. Okay, so this damping ratio can be determined experimentally with some simple tests. So you just look at the amplitude of successive waves, so I won't go into too much theory on it, but it's quite easy to determine. Okay, so if I do, it doesn't have many result frames. Okay, so that's... Alright, so normally I'd have more result points stored, but for some reason there isn't that many. So you can see that the wave sort of sweeps along. So the fingers that are shorter, they die out much quicker, whereas the longer arms take a few more waves to sort of die out. And put in a more reasonable scale factor. Okay, so it's a bit hard to see with that one there. I'll see if I've got another solution that's got more frequency content there. Okay, so here I've got a harmonic analysis. So here I'm just putting in a force at each one of these tips, and I'm going over a range of frequencies, and I'm seeing what the response of each one of these fingers is. So it will basically pick up the peak of each one of those fingers there. So we'll put all of those graphs into one. So some of them have double peaks because it's got sort of two modes over that range. So you can sort of use this to determine your response as well. If you've got an excitation that will go over a frequency range. Okay, so these are just some different ways of sort of defining the damping. So we put in the beta value. So normally we can calculate the damping ratio out of there. So the logarithmic decrement you can normally determine if you've got some base measurements. Or otherwise, if you know the damping ratio, you can sort of figure out the logarithmic decrement as well. Okay, so this beta value, so because that's constant, that implies a frequency-dependent damping ratio. Okay, you can sort of do it the other way around, where you do a constant damping ratio, and that means that the beta will vary with frequency, and the solver automatically calculates that based off your inputs. Okay, so here this is just reiterating. So the stiffness coefficient that is calculated here, that remains constant across all of your frequencies. Okay, so we're just basing it off this particular combination of frequency and damping ratio. Okay, so this sort of shows the effect. So with the much higher frequency, so the damping ratio is basically a measure of the two successive waves. So I think the first finger is based off the successive peaks dying off by a factor of 2. So for the higher frequencies, because that logarithmic decrement is higher, it dies off much quicker. So the ratio of the successive amplitudes is a lot higher than a factor of a half. Okay, so other sorts of simulations we can do. So you can do a block dropped on a wheel, or something falling on something else, and we can have an impact analysis. So generally we don't simulate the free fall. So you normally calculate the velocity just before it's about to hit, and then that's the phase that you simulate. Okay, so I've got a model of a ball dropping onto a plate. Okay, so there's a modal analysis here to figure out what sort of frequencies this structure has, because I want to sort of capture the bouncing around of the structure. Okay, so here I specify an initial velocity. Should show up there. Okay, it's not. Okay, so this ball is given an initial velocity that sort of will make this have an oblique impact. So the idea is that this ball will bounce off. Okay, so if I switch my animation on, so you can see that the ball will impact and then it will bounce off, and you can see that the structure is wobbling around because of the dynamic response. Okay, so if I look at the stresses on this, so you can see that there's sort of some waves, or sort of peaks and it dies off, then it goes back up. So as this plate is bouncing around, you sort of get high and then low stresses. So if you did this loading as an equivalent impact load, so you can calculate that quite easily. But that's just a one-time load application. So you won't see this sort of bouncing around. What might be of interest is how quickly that dynamic response lasts for. So you might want that to die out quite quickly, or if it sort of goes on for quite a long time, that could be quite annoying. Okay, so this is quite an easy simulation to set up. So in terms of solving time, so something like this took around 11 minutes to solve. So for more complicated interactions, so this on a scale of complexity for an impact analysis, it's quite simple. There's only one impact event. But when you have a lot more non-linearities involved, sometimes you need to switch to an explicit solution. So here this is quite easily done with an implicit simulation. So the total duration of this event is quite short. So it's 1.5 e minus 2. So we're only really interested in the impact, but if we're interested in the bouncing around, then we might need to solve for a longer time. Okay, but the important part here is that the free fall part is ignored. Okay, so the other point to point out here, so with my time step settings, so this maximum and minimum time step, so that will dictate the upper and lower range of frequencies that I will be able to capture. So as that sort of plate is moving about, so that will have a certain frequency content. So there might be higher mode waves that are passing through that, but if I don't choose a small enough time step, I won't capture those waves. So if I go back to my modal analysis that I did as a base for this, so using that, I determined the time step size that I should be using. Okay, so if you look at some of these waves, so because the ball is hitting in the middle, it's highly likely that that mode is going to be excited, and that sort of displacement is going to be in the output. So this one here maybe not, because the ball's hitting in the middle and there's basically just a rotation in the middle there. There's not an up and down movement there. Okay, so this one here, so probably the same sort of thing. Okay, so this one here might get excited because there's a maximum movement in the middle there. Okay, so based off the frequencies, you can sort of then make a judgment based off how quickly they will possibly get damped out. So if I go to my solution information, so I just press Control F and then I search for my participation factor table. So in the, what was the direction? In the Y. Okay, so I look for the Y direction. So you can see that the total that I've captured is quite low. So because of the way this structure is supported, so it's got fixed supports on those sidewalls, it's highly unlikely that those sidewalls will move very much. So it's really only the this top part here that's going to have a lot of movement. So if I wanted to try and capture 80% of that total mass, I'd have to capture quite a lot of modes to capture that response. And doing that's not really going to add any extra value to my solution. Okay, so I mean you can see that the sidewalls do move, but there's no real, if you like, frequency content in there that's really of any significance. Alright, so with the mode superposition method, so it's linear, but it can be much faster to solve. So the way we determine what frequency content we capture with the mode superposition is based off the frequencies in our base modal analysis. So probably an analogy you can use is if you've got an orchestra with many instruments, each instrument will have a particular frequency content. So if you remove some of those instruments, so let's just say there was an instrument that played outside the audible range. So whether that's there or not, it's not really going to make much difference to what you hear, because you can't hear the frequency. It doesn't make any difference to the perceived response. So excluding, because they're excluded, they won't be there. Whereas with a full method, the way you exclude it is with the time step. So all of the frequency content will be there, just whether or not you capture it is based on your time step. So in terms of how that relates to, say, my orchestra analogy, is if you're doing a recording, if you use a very, very low sample rate, lower than the audible range, it's going to distort the signal. So if you have, I'm not sure if any of you are old enough to remember the days of MP3 files with very low sample rates. So if you had something that was sampled at, say, 8 kilohertz, it sounded really crackly and crappy. Whereas sort of CD quality was, I think, 44 kilohertz, and that picked up enough response for you to hear a very clear signal. Okay, so with the time step for a mode superposition, so it's a limitation of the solver, but it has to remain constant. So it will. So normally you know what frequency content is there, so you choose your time step to capture that. Whereas with the full method, you can let the time step adjust to capture the dominant frequency at that particular point in the solution. So as my plate is initially starting to vibrate, there might be a certain frequency content that's there, and the solver can adjust the time step to pick that frequency content up. Okay, so in the solution information, it prints out at every time step what the dominant frequency is, and then also how many points per cycle. Okay, so here it's got response frequency and whatever that is, and then the number of points per cycle. Okay, so the solver normally likes to have at least 20 points, but sometimes it will adjust the time step anyway. Okay, so here there's the frequency. Okay, so it's got 14 points per cycle. So normally the recommendation is to have at least 20. The solver, I think, only requires around 10, and only when it gets below that will it adjust the time step if you've given it the ability to do that. Okay, so that's the end of the presentation. So there's a few workshops that we'll do. So I think there's let me just see. So we'll do there's a modal analysis, and then there's a pre-stressed modal, and then there's I think there's a dynamic analysis as well. So for those of you that don't have accounts, I will bring these things around. So there's basically four workshops. So we'll bring up the order of the presentations on the other screen in a few minutes. So yeah, we'll get started on that in a minute. Okay, does anyone have any questions?
With that wall bounce, and the animation had 2 lines on the graph.
Yep.
What
Okay, so one is basically the maximum of whatever it is you're plotting, and the other one is the minimum. So over that whole structure, oh, that's not the one. Okay, so anywhere on this structure there'll be, at any point in time, there's a maximum value and a minimum value. Okay, so because that's scoped to everything, so the minimum is on the ball, which is basically nothing. So if I did something on here, I'd still get those 2 curves, but instead of it being 0, or it is 0, because there'll always be somewhere on there that's quite low. So, I mean, it's normally the maximum one that we'd be looking at. So unless you're plotting something like a minimum principal stress, then you'd have highly negative values, and the minimum is the one you'd be looking at there.
So that red line's the minimum, is that what you're saying?
The red line is the minimum, yes. And the green line is the maximum.
So is there a reason why you've got a lot of times the minimum at the beginning of this?
I mean, the time step should be lined up. So I mean, if I stop there and I zoom to that range, so the dots are at the same point.